Polar representation of complex numbers.
All right, so we want to look at under the complex numbers, the algebra. We want to look at the polar representation of the complex numbers. The polar representation of the complex numbers. We've already established the fact on complex numbers. So we want to look at how we can represent complex number in the polar form. So we said complex number is represented by x, which gives you x plus iy, where the x here is the real part of the complex number and the y here is the imaginary part of the complex number. And take note, the I here is simply equal to the root of -1. So the I here is the same as the square root of what? Of -1. That is at the imaginary part. Now, if you understand this, then how do we present a complex number in a polar form? So we want to understand that we are doing this because in representing it in the polar form, it proves easier to manipulate. It proves easier to manipulate. And what it means that in the polar representation of complex number, we also make use of complex exponential function. You make use of the complex exponential functions. Make use of complex exponential functions in the complex number. So for example, if we have the exponent of z, which in some books you see exponent z. That is, we have e exponent z. Then we can say the exponent of z is 1 plus z plus z squared, all divided by 2 factorial. So this z is divided by 1 factorial. And we know that 1 factorial is 1. And any number divided by 1 is the same number. Okay. Plus z cubed, all divided by 3 factorial, plus to infinity zn divided by what? The n factorial. So in polar representation, we make very use of what? Exponential function. Anytime you have an exponential function, this is how you expand it per binomial theorem. Okay. Now by multiplication. So by multiplication, what happens is that if we have two of these, that is, let's say e of z1 multiplying exponent of z2. So you have exponent of a complex number 1 multiplying an exponent of a complex number 2. Then we can say per laws of indices, per laws of exponential functions, when the e are the same, when the bases are the same, then we just what? When it's multiplication, we add the what? The exponent. But when the bases are the same and it's division, then we subtract the exponent. So from here, because the bases are the same, then we have e into bracket z1 plus what? Z2. That is in terms of multiplication, and this is for all z values, which is equal to I theta, imaginary part of a theta, and the real part of what? A theta. So this is valid for all values for which z is equal to I theta, and also real for a real number theta without the imaginary part. All right. So now let's look at when it is valid for I theta. How do we go about it? So when we have e is equal to I theta, then we'll be having 1 plus I theta minus theta squared over 2 factorial plus I theta cubed divided by 3 factorial plus So now, when you do this, what do you see here? What do you see here? What you like here is that because this part, it is ei. When we establish the fact that when it is e of z, we get 1 plus z squared over 2 factorial plus z cubed over 3 factorial and those kind of things. Now, we are representing the z here by this number, which is I theta. Okay. And now when we say with the I theta, take note that I is equal to the square root of what? -1. I is equal to the square root of what? -1. So now, when you put I over here, that is z. So now here becomes I theta, which is at this part. Now z square here in terms becomes, so the z square here now becomes I theta all square. I theta all square. So now when you multiply this, you are getting what? I square theta what? Square. And I squared gives what? I squared is the same as what? Root of -1 or what? Square. Or in short, I squared is equal to what? -1. So the -1 will now multiply the theta square, which is giving us negative what? Theta square over 2 pi. That is why we didn't see the I here. Okay. And this part to the I will come because we get what? I cube. So Z cube will give what? I cube, which is equal to what? Times theta cube. And I cube is the same as what? I cube will give you I. I cube will give you I. So we put the I there and we get what? Our theta 3. So that's how we got it. So you realize that when the number is even, we'll be getting loss of what? Of the I into 1. And the sign of the addition will be changing as it continues. So in summary, when you continue, you can have some imaginary parts and you can have some, when you continue, you can have some imaginary part and you can have some real part. So now, when you do it, you will get 1 minus theta squared over 2 pi plus theta 4 over 4 pi minus plus, you get the imaginary part. So what I mean is that all those that takes the even squares will be a real part because there will be no I over there because the I will tend to become what? -1 or 1. So now, but the odd numbers, you get the I. So you get theta itself here minus theta 3 over 3 pi plus theta exponent 5 over 5 pi, 5 factorial, sorry, over 5 factorial, and it continues like that. But because of the presence of the I here, the whole of this part now becomes the imaginary part. So you can take your time and you expand it to maybe I5 and you know how this came about. And the whole of this part will be what? Our real part. So now, when we expand this one very well, what happens is that when we consider this real part of the equation, e exponent I theta now becomes this real part of the equation, 1 minus this, 1 minus that. In terms of its angle form, it is the same as the cos of what? Theta. So in terms of, when you want to use trigonometry to represent this, are you getting it? The imaginary part, the real part here is the same as the cos of the angle theta. The cos of the angle theta. Alright. Plus, and this part, because of the I, being it what? Because here is taking the even number, and here is taking the odd number, it is I sine of the angle theta. It is I sine of the angle theta. And this equation here is what we call the Euler's equation. This equation here is what we call the Euler's equation. Is the Euler's equation. The Euler's equation. So now, with the Euler's equation, we can expand it and we have, that is E exponent I n theta to get cos of n theta plus I sine n theta. This is for all n values. For all n values. For all n values. For instance, you might have maybe E of I 3 theta. Then when you expand it, you get 3 cos 3 theta plus I sine 3 theta for all n values. And when you do this, from this equation, we can deduce that. So from that equation, we can make a deduction that anytime you have a number multiplying E of I theta, so let's say you have a number R or a real figure R multiplying the E of I theta, then when you expand it into the equation, it becomes R, and the E of I theta gives this value. So it becomes R multiplying cos theta plus I sine what? Sine theta. So now when you do this, the r cos theta, this part is now x, and the r I sine theta becomes our iy, and that is how we represent what? Our complex number. So now what happens is that we'll be having our normal z. We're having a normal z. So now what happens is that we have a real part of the equation, and we say that real part is called r, and the imaginary part of the equation, that one is e exponent what? I theta. So now if that is the case, and we want to multiply a real part by the imaginary part of the equation, we say we are getting what? R into bracket cos theta plus I sine theta. And now when we do this and we expand it, what we are getting is what? R cos theta plus what? IR what? Sine theta. And when you do this, because of the real part, this one becomes x plus our I, and r sine theta becomes our y, and this is equal to what? Our complex number. So therefore you can say that z is therefore equal to r e I theta. R e I theta. R e I theta. So now in a polar form, in representing a exact number, so in polar form, a complex number is represented as z is equal to what? R e I theta. R e I theta. And now, when you have it represented this way, what happens is that you have to identify the modulus and the argument of the complex number. The modulus and the argument of the complex number. So now, anytime you're able to represent a complex number in such form, or in this form, what happens is that the absolute value of the r comes with the absolute value of the z, that is the modulus of the z, and theta with what? The argument. So the argument of z. So now what happens is that the modulus of the complex number is the r. So r becomes the modulus of the complex number, and the theta you get here is the argument of the complex number. So take note. Anytime you have your complex number represented this way, your modulus of the complex number z is what? Is r. And your argument of the complex number is what? The angle theta you have over here. The angle theta you have over here. But sometimes so let me present it here well for you. So now what happens is that you have our z is equal to r a I theta. So now your modulus now, this is the polar form. So the modulus now becomes the r, and your argument of z is now what? The theta. So now what happens is that the theta here is in the range of what? Negative pi theta to what? Less than positive pi. We've done this in previous videos, so you can go and change the range. But since the rotation, so you can write this, since the rotation by theta is the same, since the rotation of theta is the same as the rotation, since the rotation of theta is the same as the rotation of 2n pi plus theta, since the rotation of theta, of this theta, is the same as 2n pi plus theta, where n is an integer, then we can have our polar form represented as r e exponent I theta, which is equal to, so this theta, which is represented now becomes 2n pi plus what? R theta. So therefore, we can extend and we say that, IE, which is our theta, can also be the same as REI into bracket 2n pi plus what? Our theta. Because their rotation is the same. The rotation of this angle and the rotation of theta is always the same. So 2n pi plus that. Alright, so now let's look at how you can multiply complex number in the polar form and how you can divide complex number in the polar form. So quickly, I want to look at multiplication and division of complex number in polar form. Okay, so let's look at the multiplication and division of complex number in the polar form. So in the polar form, what happens is that so let me just divide it and let me do the multiplication here, and we do the division at the other side. So with the multiplication, let's assume you have z1, which is equal to r1 e of I theta 1, and another complex number z2, which is equal to r2 e of I theta 2. And we said we want to multiply z1 multiplying z2. So if you want to multiply z1 multiplying z2, then we will get r1 ei theta 1 multiplying r2 ei theta 2. So now what happens is that when you get this, when you get something like this, you can just take the real part and multiply the real part, and you later deal with what? The imaginary part. So when you have something like this, what happens is that the real part, you do the real part, which is r1 multiplying r2, and they all come to multiply. Because the imaginary part, the e and the e, they are of the same base, then we just take one of the base and we add their exponents. We take one of the base and we add their exponents. So now e exponent I into bracket theta 1 plus what? Theta 2. So anytime you want to multiply a complex number in the polar form, this is how you go about it. So you simply r1, r2, e of I into bracket theta 1 plus what? Your theta 2. So if you have something represented in this way, then you can send it into the cos function and the sine function. So send it into the cos function, because r1, r2, or into bracket cos of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. Alright, sorry. So when you do this, why? Because we already established the fact that if you have e of I theta, then it's the same as what? The cos of theta plus what? I sine of what? I sine of theta. So now the theta here is now what? Theta plus 1. So that's how we are getting this value. All right, so let's look at the division. Let's quickly look at the division. Okay. Sorry, the marker is not working well. So let's quickly look at the division 2. So with the division 2, assuming you are having z1 is equal to r1 e I theta 1, and you have z2, which is equal to r2 e I theta 2. So this is what you're having. And we said find z1 over z2. So to find z1 over z2 is very simple. It's 1 r1 e I theta 1 all divided by r2 e I theta 2. So now when you do this, you deal with the real part of the equation. So r1 divided by r2, and you take only one of what? The imaginary part. And because the bases are the same and they are divided, you take one base and you subtract the exponents. Are you getting it? So now it becomes e I into bracket theta 1 minus what? Theta 2. That is the law of exponential functions. Okay. So now if you want to extend this into the form of the sine and the cosine functions, then you can say r1 over r2 e of I theta 1 minus theta 2 is equal to r1 over r2 multiplying cos of theta 1 over minus theta 2 plus I sine of theta 1 minus theta 2. Last one, sine of theta 1 minus theta 2. And this is how you can divide complex numbers in their polar forms. Okay, so we move on to the application, and during the application, after the application, we'll solve some examples under this. Thank you for this class.